So without avalanche, the APD is biased at a voltage of, in this case here, above 200 volts. Then a photon comes in. So the capacitors discharge in the APD into the resistor. So there's a voltage increase at this resistor. So consequently, there's a voltage drop at the APD that you can see here. And here the APD goes below single photon sensitivity. So you see that the bias of the APD is lowered at the level or below breakdown voltage. And then we end up in linear mode here. So the avalanche is quenched. We are back in linear mode. The bias voltage is below breakdown voltage. And then the capacitors slowly recharge. In our case, it takes about 1 microsecond, after which the detector is available again to detect a single photon. But if now you apply CW bright illumination, what happened is that photons keep coming back, and each little avalanche resets the voltage below the single photon sensitivity threshold. So under bright illumination, the detector is kept in the linear regime, where it works as just a linear amplifier. So as we saw on the previous slide, it's completely blind to single photons. But you can still make it click controllably if you apply a classical pulse above the comparator threshold recording the clicks. And you have an illustration here. It's an oscillogram showing the detector output as a function of input illumination. We apply here about 50 microwatts power, so we are well above single photon levels. And as you can see, the detector is completely blind. There's absolutely no click. The detector works as a linear amplifier below breakdown voltage. No click, the detector is blind. Now, if we apply pulses of typically few milliwatts power, then the signal here goes above the threshold of the comparator, and you can see the detector clicking with unity probability and very low time jitter. So you have a very tight control of the detector. And this is the intensity I0 at which the detector clicks. And what this oscillogram doesn't show is that if instead you apply a pulse of intensity I0 divided by 2, your detector will be completely blind. So we get in the what-if scenario that I mentioned before. The detector always clicks at intensity I0, and if you apply half the intensity, the detector gets completely blind. So you have a case to launch the intercept-resend attack, the fake state attack. And it is illustrated here. So so basically the general idea is that Eve will force her detection result onto Bob by first using a control generator, sending bright illumination into all detectors to blind them. So all 4 detectors are blind. And then we consider the case here where, again, the detector recording vertical polarization clicks. What Eve has to do to address this detector is to send a fake state generator with vertical polarization and 2 times the threshold intensity at which the detector clicks. So let's follow the path of this fake state. So this fake state is split in 2 at the beam splitter. So here we get a pulse of intensity I0 and vertical polarization. So the PBS will route the signal into this detector, which will click. There will be no intensity in this detector, it will remain blind. Now, in the second measurement basis, the pulse of intensity I0 and vertical polarization will be rotated by 45 degrees at the half-wave plate. And then at the PBS, it will be split in 2 parts of intensity I0 divided by 2. And at this intensity, as we saw before, the detector gets blind. Okay. So, question is, does it work in practice? Well, for that, I will let Chin present the attack on a real quantum crypto system.
Thank you. So now I would like to present you a working eavesdropper we have built against the existing QKD system. So firstly, I would like to describe this QKD system under attack. This QKD system is built by National University of Singapore. In this QKD system, there is an EPR source which is located close to Alice, generates pairs of entangled photons. And for each entangled photon pair, one photon is sent directly to Alice, and another photon is sent to Bob by the transmission line. And to detect the photons, Alice and Bob both use the same detection unit. We have seen this before, the same detection unit. And EPR source, EPR stands for the first letter of Einstein, Polosky, and Rosen, who have found this funneling property of entanglement. So for entanglement photons, if one measure one photon here, he will automatically know the measurement result of another photon at another place. So that means the photon pair is in a well-defined state, but each photon is in an undefined state. And this equation can describe this property. So that means if one photon is in the vertical polarization state, the another photon is in horizontal polarization state for sure. And if you measure the photons in another basis, say if you measure in the diagonal basis, if one photon is in plus 45 degree and another photon is in minus 45 degree for sure. So one photon is always orthogonal to another photon. This is a property of entanglement photon pair. And this is a structure of the EPR source. So here, a blue light generates from a laser diode focused in a BBO crystal. And from here, one blue photon comes in and two red photons comes out. And through the single mode fiber, one photon sent to Alice and one photon sent to Bob. And here you can see the picture of the EPR source. And for Alice and Bob's detector, we have brought one detection unit which is really used in Bob, and you can see it later in the demo. And here on the picture, it shows the inside view of the detection unit. You can see on the picture that this is a 50-50 beam splitter, and followed by the two polarization beam splitter. And here is a half-weight plate, and there are 4 avalanche photodiodes kept in the housing. So again, this is a normal QKD system. To launch our attack, we cut the transmission line and insert our eave. And our eave contains a replica of Bob to receive the photons, and the rest is a fixed generator to control Bob. The fixed generator mainly contains 5 laser diodes. The first laser diode is aligned to the circular polarization state, which will keep all the 4 detectors of Bob blinded. And for the rest of the 4 laser diodes, each of them is aligned to a certain polarization state, which target one detector of Bob. And all the 5 channels combined together by 50-50 coupler and goes to Bob. So now, for example, if Eve receives a vertical click here, the output will trigger the corresponding channel of pulse generator, drives the corresponding laser diode to generate the optical pulse to make a single click at the target detector. This is very simple. This is just how we get the full control of Bob. But this scheme didn't work perfectly.